This is part C for Unit 3 for our course on statistics. And we've been talking about 3 different types of studies about means. And in this third section, we're going to talk about a type of study that we could call a two samples study. And this could also be called a independent samples design or a two groups design. And this is going to involve looking at a simple contrast. And you may recall that I said this entire unit was supposed to be a unit all about doing simple contrasts. That is, where we make a contrast between two groups. But up to this point, I have not been talking about simple contrasts. The first type of study we talked about was a single sample design, and then we talked about a paired samples analysis, but these did not involve doing a simple contrast. And essentially, I talked about these first 2 types of studies to lay a foundation so that we can talk about this third type of study, a two samples design, that does involve making a simple contrast. So now that we have this foundation in place, we can look at a two sample study that's going to involve making a simple contrast where we make a comparison between two groups. And a simple contrast will be one of the most useful and basic types of analyses that we can do in scientific research in psychology or neuroscience or medicine. It can involve investigating a difference between two naturally occurring groups. For example, maybe I wanted to look at a difference between, say, women and men in how much they like to watch movies about, say, giraffes. Now, note that if I have a sample of, say, heterosexual couples, and each couple had one woman and one man, and I was looking for differences between the men and the women in the couples, well, that would be a case where I would use a paired samples analysis, like we talked about in the previous section. But here, I'm going to be talking about something different. So here I would talk about a situation, if I was looking for a gender difference, it would involve a situation where I have one group of women and a separate group of men, and the women and men are not related to each other, and there would be no way to make meaningful pairs between them. So in this case, I would say I have two independent samples, which is one reason why we could call this a two samples type of analysis. And so what I'm going to do is I'm going to make a simple contrast between these two groups, one group of men, say, and one group of women, and these two groups are not related to each other. Now, the most common use of a simple contrast is going to be where I do an experiment or a clinical trial where people are randomly assigned to two groups. And I might randomly assign people to a treatment group and to a control group to see if there's a difference between those two groups on some outcome variable. So the most common use of a two samples design, the most common place where we're going to be doing simple contrasts, is where we're doing experiments or clinical trials and we're randomly assigning people to two groups to see if there's a difference between those two groups on some outcome variable. Say, for example, I had a theory that if I made children wear costumes, that would make them happy. That by forcing children to wear costumes, that would increase their feelings of happiness. And maybe I wanted to test my theory, and so I could do a study where, say, I get a sample of 8 children, and I randomly assign each child to be in either the treatment group or a control group. And the children in the treatment group are all forced to wear costumes, and the children in the control group are not forced to wear any costumes. And then I see if there's a difference between the two groups in their levels of happiness. So maybe on the screen we see these 4 children on the left. Maybe those are the 4 children in my treatment group who were forced to wear costumes. And then on the right, we see 4 children without costumes. So maybe those are the 4 children in my control group. Now, one thing to note is that in this example, I have exactly 4 children in each group. But to do this type of analysis, we do not need to have equal sample sizes in each group. I could have one group that's larger and one group that's smaller, and that would be perfectly fine. So it would be perfectly fine if I had, say, 8 children in one group and 4 children in the other. These group sizes do not need to be equal. And as always, I'm showing you a very small sample size. I'm showing you a study with just 8 children. And that would be a very small study. If I really wanted to investigate a difference between two groups of children, I would probably want to have a much larger sample. But I'm giving you examples with small sample sizes so that everything fits on the screen in my PowerPoint slides. And one other little thing to note here is that in my pictures for children with costumes, these pictures show the children all wearing different types of costumes. And if I really wanted to do a valid study, it would be important for all the children in my treatment group to get the exact same treatment. So they would all need to be forced to wear the exact same costume to make this a valid study. So it would be somewhat problematic if I did a study and gave different costumes to different children. So let's take this example though and see how we could do a contrast. So if I'm doing a 2 samples study and I'm going to test a contrast between 2 groups, in this type of study I'm going to have 2 variables. One variable will be a dichotomous variable indicating group membership. So I will have a dichotomous group membership variable, and then the other variable will be a numerically scaled variable that ranges between high and low, and it will be the variable for which I think there will be a difference between groups. In other words, if I were doing a clinical trial or an experiment, it would be my outcome variable. In this example, if I think there's going to be a difference between 2 groups of children in their levels of happiness, well then levels of happiness would be that numerically scaled outcome variable. And the way we will set this analysis up, we're going to think in terms of using group membership to predict that numerically scaled outcome variable. And so because that numerically scaled variable will be the thing getting predicted in our equations, we're going to call that variable y. So in my example here, I have at the top y equals levels of happiness. Variable y is the level of happiness for each child. So maybe after I've given the children the treatment or no treatment, I measure their level of happiness. Maybe I have an observer watch the child for 10 minutes and give a rating of the child's level of happiness. And then each child will have a score on this y variable, which is that child's happiness when the child's happiness is assessed. So y is level of happiness. It's a numerically scaled variable, and every child will have a score on that y variable. So if y is the numerically scaled outcome variable, x will be the dichotomous group membership variable, and every single person in the sample will get a score on variable x. So I have at the top here x equals group membership, and I'm going to use numerical values to label each group. In this case, the numbers don't mean that one group is higher than another. Group 1 is not higher than group 0. We can think of these as simply using numerical values as labels or names for each group. So in this example, I'm going to say that my treatment group is group 1 and my control group is group 0. So I'm going to say everyone that's in this treatment group, all the children that are forced to wear costumes, they're in my treatment group, and so their score on the x variable is 1. X equals 1 for every single person in the treatment group, and x equals 0 for every single person in the control group. So now you see we have a sample of 8 children, and every child will have a score on 2 variables. Every child will have a score on the x variable, which is either a 0 or a 1 based on group membership, and every child will have a score on the y variable, which is the child's level of happiness, that numerically scaled outcome variable. So here's what a hypothetical data set might look like for this type of study. So once again, every case has been placed on a separate row. In this case, I've got these children, and every child is placed on a separate row, and every child has a score on 2 variables. Every child has a score on y, and every child has a score on x. And x indicates group membership, and y is the child's score for the child's level of happiness. So for this first case here, that child was in group 1, and group 1 was the treatment group, and that child's happiness was a 3. I guess that would be that child wasn't very happy. That child had a very low level of happiness. The second child was also in group 1, and that child had a score of 4 for happiness. Just a smidgen happier, but not much. Third child was also in group 1. That child had very low happiness, way down at a 2. But for example, let's look at this child. Here's a child in group 0. That was the control group. That child's happiness was way up at a level 8. And here's another person in group 0 that had a happiness of 8, and so forth. So we see each child has a score on X, which is either a 0 or 1, which indicates group membership. So X is group membership, and in this case, it's just a 0 or a 1. Those are the only options. It's a 1 if you're in the treatment group, and a 0 if you're in the control group. And the Y variable, that's that numerically scaled variable. In this example, it's the child's level of happiness. Now, one thing that I'm going to do here, and make a note of this, and throughout this entire unit and this class, I'm always going to be saying that group 1 will be listed first, and group 0 will be listed second. So I'm going to use 1s and 0s, and the very first group, I'm going to call that group 1, and whatever group is second, I'm going to call that group 0. And if I have a treatment group and a control group, I'm going to call my treatment group group 1, and my control group group 0. Now, we don't have to do it this way. If we wanted to, we could use any two numbers as labels. I could say group 1 and group 2 if I wanted to. Or actually, if I wanted to, I could say, maybe I could say one group is called group 5.6 and another group is called group 1042.8. I could use any two numerical values I wanted to label my groups. But if I follow this format, it will make it easier for us. It will both be consistent, so it won't be confusing, so this consistency will help. And later on, we're going to be doing some things where if we follow this format where the first group is always called group 1 and the second group is always called group 0, if we follow this pattern, it's going to make some things come out a lot easier for us when we do our analysis. It will make things a lot easier. So I'm always going to follow this format where the very first group will be called group 1, and then the second group will always be called group 0. And for this entire class, that's the way I'm going to do things. Now, if I'm doing a two samples study and I'm making a contrast between two groups, then the most basic question at hand is simply whether there's a difference between the means for the two groups. So I could calculate the mean for each group and then see what the difference is between those means. For example, we have the 4 children that were in our treatment group, that's group 1, and we could calculate the mean on variable y, that is the happiness variable for that group. So if we take 3 plus 4 plus 2 plus 3 divided by 4 to get the average level of happiness for that group, and the mean for that group comes out to be 3. So I have up here y bar with a subscript 1, that's the mean on the outcome variable y for group 1, is equal to a 3. That's their average level of happiness. And then we could go to our control group, group 0, and calculate the average happiness for that group, 8 plus 8 plus 7 plus 9 divided by 4, and we get an average happiness level of 8 for that group. So I have y bar for group 0 is equal to 8. And then we could simply calculate the difference. 3 minus 8, y bar for group 1 minus y bar for group 0 gives us -5. These two groups are 5 units apart from each other. That's the size of difference in their happiness scores. Now, for each different type of study that we've been considering here, I've been giving you linear equations, and I've been talking about how we can use these linear equations to address the important questions at hand. And the reason why I've been talking about these linear equations is because if you understand the principle for how these linear equations work, you can use that principle to address a wide range of research questions. If you understand how these linear equations work, you can use these linear equations to address just about any type of research question you might face. So, what are the linear equations that we will use if we're doing a two samples study and we're making a contrast between two groups? Well, if I'm doing a two-sample study, the linear equations will look a little bit different from the linear equations we've been looking at before. So let's break it down and look at it one step at a time, and let's start with just the equation for variance in a sample. And at the bottom of this page, I have two equations, and these are actually both versions of the same equation. These are both versions of the equation for variance in a sample. I simply have one version without the hat over the y, and another version that has a hat over the y. So these are just two versions of the same equation, one without a hat, and as we see, when we take the hat away, we have an e on the end of our equation, or we have a version that has a hat over a y, and there's no e at the end of that equation. Also note, in these equations, I don't yet have all these subscripts we're going to use. Eventually, I'm going to add a subscript with the letter S to indicate sample, and I'm going to leave that off right now just so we can focus on these equations and see how they work. And then eventually we'll add all the subscripts, and then eventually we'll look at the equations for sampling error variance in a population. So first, let's just look at these equations for variance in a sample and see what we have. So I have here the score on y for individual I. So every single child has a score on happiness. Y is the happiness variable, so every child has a score on the y variable. And so I say the score on y for individual I is equal to the mean for our control group, the mean for group 0. In this example, we just looked at that and saw that the mean for group 0 was an 8. So I'm actually using that mean right there, the mean for my control group, plus the difference between the two means, the mean for group 1 minus the mean for group 0. That's that thing we looked at that was in this sample, that difference between the two means was a -5. So the difference between two means, and then I'm going to take that difference between two means and multiply it by the score on x for individual I. So each person has a score on x. It will either be, the score on x will be a 1 if you're in the treatment group, and it will be a 0 if you're in the control group. So it's either a 1 or a 0. So I'm going to take that difference between the two means and multiply that by a person's score on x, the score on x for individual I, plus the error. That will be the error for individual I. So that's what the formula looks, that's what our equation looks like without the hat, or I could put a hat on it and say the predicted score on I, or the predicted score on y for case I, is equal to the mean for our control group plus the difference between the two means, y bar 1 minus y bar 0, times the score on x for individual I. So that's what the equation looks like. This is our equation for variance in a sample. Let's see if we can unpack this equation a little bit and see exactly what's going on. It might look a little bit funny at the moment, so let's see if we can understand why this equation looks the way it is and what it's doing. So again, here is our equation for variance in a sample, and this is the version that has the hat over the variable y. So we say the predicted score on y for individual I is equal to the mean for our control group, that is the group 0 mean, plus the difference between groups times the score on x for individual I. And notably, we could think about this difference between two means as the difference between groups, the size of difference between groups. Another way of saying the same thing, it's the expected increase for group 1. That is, if you go from the control group, group 0, to the treatment group, group 1, how much on average does happiness increase? That's the difference between the two means. So in this case, if we take the mean for group 1 minus the mean for group 0, in our example, we got a -5, meaning that happiness went down 5 points when we went from the control group to the treatment group. So we could say the expected increase if you go from group 0 to group 1, the expected increase for group 1 in this example was a -5. So these are the components of our equation. So essentially what this equation is doing, it's setting things up so that each person's predicted score will be equal to the mean for whichever group that person belongs to. that is, the predicted score on y for individual I will be equal to the mean on y for whichever group person I belongs to. So for example, we have the people in our treatment group, the children that were forced to wear costumes, the treatment group. The mean happiness level for the children in our treatment group was a 3. Y bar for group 1 was a 3. So that means for every child in group 3, that child's predicted score on y, that child's predicted score for the child's level of happiness will be a 3. We're going to predict the mean for group 1 for every child in group 1. And for the children in our control group, the mean for the control group was an 8. The average level of happiness in the control group was an 8. And so for every child in the control group, we're going to predict that their happiness will be an 8. So if you're in group 1, the mean for group 1 was a 3, and so for everyone in group 1, their predicted score on y will be a 3. And for people in the control group, group 0, the mean for the control group was an 8, and so for everyone in the control group, y hat will be an 8. Note how previously we've talked about how we can use just a single mean to predict people's scores, and now we're using something more than just a single mean to predict people's scores. Now we're using group membership and means from two different groups to try to predict people's scores. Rather than simply saying your predicted value is equal to the group mean, we're saying, well, if you're in this group, your predicted value is equal to the mean for that group, and if you're in a different group, your predicted value is the mean for that group. So your predicted value is the mean for whichever group you're in. Let's see how this equation works. So if you're in group 1, in our example here, so if we have a situation where the mean for group 1 is a 3, and the mean for group 2, for group 0, I should say, is an 8, and the difference between those two means is a -5. So if we plug this equation in for anyone in group 1, if you're in group 1, your score on x is going to be a 1. So this equation becomes, here we'll say we'll take the mean for our control group, and our control group had a mean of 8. Let me erase everything here so we can see what we're doing here. So I'm going to take the mean for my control group is equal to an 8. And so I'm going to plug that in right here. And then the difference between the two groups, y bar 1 minus y bar 0, is a 5. So I'm going to plug that in right here. And then if you're in group 1, your score on x will be equal to 1. So I'm going to plug that in right here. And if I take 8 plus -5 times 1, that gives me 3. And 3 is the mean for our group 1. If you're in group 1, the mean for group 1 is a 3. So this works out right. So it says this equation works out so that if you're in group 1, it's going to return a predicted value. Your predicted value on I, for individual I, for anyone in group 1 is going to be equal to 3. That is, it's going to be equal to the mean for group 1. Let's see how this works if you're in the control group. If you're in group 0, in that case, your score on x will be 0. So the first parts of our equation stay the same. We still have our equation where we say it's the mean for the control group, which is an 8. And so I'll plug that in there. Then we're going to take the difference between the two groups, y bar 1 minus y bar 0, and that was a -5. So I'm going to plug that in right there. So note that it's 8 plus -5 times something. That part stays the same for both equations. But if you're in group 0, your score on x will be a 0. So I'm going to plug in 0 right here. That's your score on x. That's your score on x for individual I. That's what that is right there. And so now I have an equation that says it's 8 plus -5 times 0, and anything times 0 is just going to drop out. So that's going to drop out, and I'm just left with a score of 8. And of course 8, that is the mean for people in the control group. So note what happens here. When we use this equation and we plug these values in, we end up with a situation where the predicted value for anyone in group 1 is going to be equal to the mean for that group, and the predicted value for anyone in group 0 is going to be equal to the mean for that group. So that's what these equations are doing. And here is the full version of the equation for variance in a sample. And here I've written the equation out with the version that does not have a hat over y. I'm using the actual score on y and not y hat. And then when I take the hat away, of course, I add the error to the end of my equation. So this is the version that does not have a hat over y and has an error at the end of the equation. And also, I've added the subscript s to clarify sample. So I've added that s for sample subscript. So putting it all together, we have the actual score on y for individual I from sample s. That is y subscript is is equal to the mean for group 0 from sample s, that is y bar with a subscript 0s, plus the difference between the two means, that is the difference between the mean for group 1 from sample s, y bar subscript 1s, minus the mean for group 0 from sample s, y bar subscript 0s, times the score on x for individual I from sample s, plus the error for individual I from sample s. So that is our linear equation for variance in our sample. Now with that equation, you should probably be able to identify, see if you can do this, can you identify what components of that equation are variables and what components of that equation are parameter estimates? So what are variables and what are parameter estimates? So a variable is anything that can potentially vary across persons. And every variable will have the subscript is. There will be an I in the subscript to indicate it pertains to an individual and that different individuals can have different values. So YIS, scores on Y, that's one variable. And then XIS, people can have different scores. It's either going to be a 1 or a 0. In this case, there's only two options, but people can have different scores on X. And so X is a variable. And then we have our error. As we'll see, this is actually how far people deviate from their predicted value. That is how far they deviate from their group mean in this case. So we've got three variables, YIS, XIS, and EIS. And every variable has the subscript IS, and every variable is something that can potentially differ between the different cases in the sample. So if those are the variables, what are the parameter estimates? Well, one parameter estimate is the mean for group 0. And you could say this a couple ways. We could say the second parameter estimate is the mean for group 1, our treatment group. That would be a valid way to answer that question. But to set things up for how I'm going to be talking about things, I'd like to say it this way. I'm going to say that one parameter estimate is the mean for group 0, and another parameter estimate is the difference between the two means, y bar 1 minus y bar 0. And I'm going to say those are our two parameter estimates. So one parameter estimate is the mean for group 0, and another parameter estimate is the difference between means. Now, as we go along here, we're going to see that this first parameter estimate is something we just need in the equation to make it work. And when we do our study, we really don't care specifically about what exactly is the mean just for our control group. That's not really answering an important question, but we need that parameter estimate to make our equation work. In contrast, this second parameter estimate, this difference between the two group means, well, that's the thing we really care about. That's the thing we want to know. We want to know what exactly is the difference between these two groups. That's the contrast that we really care about. So we've got two parameter estimates. One is something we just need for our equation to make it work, but we really don't care that much what it is. Another one we need for our equation, and it's the thing we really care about, the difference between the two means. So there is our equation for variance in a sample. So now what we need next is the equation for sampling error variance in a population. Let's see what that will look like. Now, for every type of study that we've been discussing, I've given you two different linear equations. One linear equation has been the equation for variance in a sample, and the second linear equation has been the equation for sampling error variance in a population. Now, if we're doing a two samples study and making a contrast between two groups, we're actually going to have two equations for sampling error variance in a population. So what we're looking at up at top here with these equations, I have the very top equation, That's the equation we've been looking at. That's the equation for variance in a sample. And then I have two equations below that, and both of these equations are two different equations, and they're both equations for sampling error variance in a population. So why do we have two equations? What's going on here? Well, recall the process that we've been using. Recall that in each case, we've started off with an equation for variance in a sample, and that equation has had a parameter estimate in it. And then we've taken that parameter estimate from our first equation, and that parameter estimate becomes the thing that's predicted in our second equation, in the equation for sampling error variance in a population. And in our equations for sampling error variance in a population, we say that this parameter estimate from our sample is equal to the true population parameter plus however much error we made in our study. And so in our current situation here, where we're doing a two samples test, where we're looking at a contrast between two groups, if we look at our top equation up here, we have two parameter estimates. And so because we have two parameter estimates, we're going to have a separate equation for sampling error variance. We're going to have a separate sampling error variance equation for each parameter estimate. So let's see what we have here. In our top equation, the equation for variance in a sample, the first parameter estimate we had here was for the mean for group 0, the mean for our control group. And so I'm going to take this parameter estimate and pull it out and make it the thing that gets predicted in a sampling error variance equation. And I'm going to say that the mean for group 0, y bar subscript 0, that's the mean for group 0, from sample S from population P. So y bar, the mean for group 0 from sample S from population P, is equal to the true population parameter, that is the true population mean, or mu, for group 0 from population P, plus the error for group 0 from sample S from population P. So I've taken that first parameter estimate, the mean for our control group, and pulled that out, and I have a sampling error variance equation for that parameter, where I say that parameter estimate is equal to the true population parameter plus the error that I make in my study. And we're going to do the exact same thing then for our second parameter estimate. Our second parameter estimate was the difference between the two means, y bar for group 1 minus y bar for group 0. So I'm going to take this parameter estimate and pull that out and make that an outcome that we predict. And we're going to say that that parameter estimate is equal to a true population parameter plus however much error we make in our study. So let's see what we have here. So I say, note that this is the exact same thing. I have y bar 1 minus y bar 0, and I pull that out. And as always, when I move down to my second equations here, I'm going to add a subscript p to clarify this is coming from population P. So I have, I'm going to erase stuff so I can go through this here. So I have y bar, the mean for group 1 from sample S from population P, minus the mean for the control group, the mean for group 0 from sample S from population P, so that's the difference between our two means, is equal to the mu, the true population parameter for group 1 from population P, minus the true population parameter for group 0 from population P, so that's the true population parameter difference between those two group means, plus the error for 1 minus 0, that's the difference between group 1 minus group 0. So the error 1 minus 0, that's the error for the difference between the two means, from sample S for population P. So that's how I would write out all the linear equations with the subscripts when I'm doing a two samples test to make a contrast between two groups. And as always, if you understand how these linear equations are working, then if I give you an example with numbers, you should be able to plug numerical values into the linear equations. So for example, let's consider case 2 in this example. This is a child up here, and she was in our treatment group, group 1, and her sadness level was a 4. So that's case number 2. Let's consider what the values would be in this first linear equation. That's the equation for variance in a sample. let's see what the values would be for that first linear equation for case number 2. So our linear equation says that the score on y for individual I in sample S. Well, this person right here, case 2, her score on y is a 4. So I'm going to plug that in right there. And then we're going to take the mean, the score on y for individual I from sample S is equal to the mean for the control group for sample S, the mean for group 0 from sample S, and we calculated the mean for our control group. The mean for group 0 was an 8. And so I'm going to put an 8 right there. And then we're going to have, next we have the difference between the two groups, y bar for group 1 minus y bar for group 0 for sample S. And we saw up here that the difference between the two means for this example was a -5. So I'm going to plug that in right here, put a -5 there. And then I'm going to take that difference between two means and multiply it by the score on x for individual I in sample S. So we're looking at case number 2, and her score on x is a 1. She's in the treatment group, and everyone in the treatment group has a score on 1 for variable x. So I'm going to put a 1 there. And so then I can say, what is 8 plus -5 times 1, and get her predicted score. And her predicted score is actually going to be equal to her group mean. So if she's in group 1, the mean for group 1 is going to be a 3, so that will be her predicted score, because this equation works so that everyone's predicted score is going to be the same as the mean for whatever group they're in. So someone in group 1, her predicted score is going to be a 3. The mean for group 1 was a 3, so her predicted score is a 3. Or if we take 8 plus -5 times 1, we get 3. So if we predict her score to be a 3, and she actually got a 4, she is 1 unit higher than what we predicted. Therefore, the error for her, she is 1 unit higher than predicted, so her error is going to be 1, plus 1. And so that's the equation that with the numbers plugged in for case 2. And then we can look at our second our equations for sampling error variance in a population. Let's look at the second set of equations, and we could say, what would these equations be with numerical values plugged in if the null hypothesis is true for this example? So we have our first equation would be the equation looking at our parameter estimate is the mean for group 0, the mean for our control group. And we say the mean for our control group, y bar for group 0 from sample S from population P, and we see up here our mean for our control group is an 8. So I'm going to take that 8 and I'm going to put it right down here and plug that in there. And we're going to say the mean for group 0 is equal to the true population parameter. And as always, we're simply going to assume the null hypothesis is true and that the true parameter is 0. So I'm just going to put a 0 there. And then how it's always going to work is that if I assume the true parameter is 0, this second equation, this equation for sampling error variance in a population, always becomes our parameter estimate is equal to 0 plus the value of our parameter estimate. So this equation becomes 8 equals 0 plus 8. If the true population parameter is 0 and we got a mean of 8, then we were 8 points higher than the true parameter. We made 8 units of error. So the equation becomes 8 equals 0 plus 8. And then we'll do this final equation, this equation for sampling error variance in a population for our second parameter estimate, which is the difference between the two means. And so this equation says the difference between the two means, y bar 1 minus y bar 0, and that's, in this example, y bar 1 minus y bar 0 was a -5. So I'll take that -5 and plug that in down here. -5 is equal to the true population parameter difference between the two means. And so the true population, and if I assume the null hypothesis is true, then I'm going to assume that the true difference is 0. So I'll put a 0 right there. I'm assuming there's no difference between means. I'm going to assume the null hypothesis is true. So I'm just going to put a 0 there. And then my error would be -5, because once again, if I assume the null hypothesis is true and that the true parameter is 0, then whatever the parameter estimate I got in my study, that's going to be the same as the amount of error that I got. So if I said, if I got a parameter estimate of -5 and the true population parameter was 0, well then I was 5 points below the true parameter if the null hypothesis was true. So once again, it just simplifies to this equation where I say my parameter estimate is equal to 0 plus the value of my parameter estimate. In this example, I have -5 is equal to 0 plus -5. Now, what about someone in the control group? How would these equations work if we look at someone in the control group? For example, consider case 7. That's the second one from the bottom here, this person right here. If we look at this person, she got a score of 7 on y, and she's in the control group, so her score on x is a 0. So this top linear equation becomes the score on y for individual I in sample S is 7. She got a score of 7 on y, is equal to the mean for the control group, that's the same as we had before, is 8, plus the difference between the two means, that's the same as we had before, is 5, times her score on x. So this is one thing that's a little different. In the previous example, for someone in the treatment group, their score on x was 1, and now for someone in the control group, her score on x is going to be a 0. So I'm going to put a 0 there, and notably that's going to mean that I'm going to take -5 times 0. Eventually that'll just cancel out if I were to calculate that equation, plus the error. So the error is how far this person deviated above or below her predicted value. So if we take 8 plus -5 times 0, that just cancels out, so her predicted value is simply 8. That is, that her predicted value is the mean for group 0. So the mean for group 0 was an 8, so her predicted value is an 8. And so if we had, by the way, so if we had the equation where I had the hat on one side, if I use y hat and I scribbled out the e, that would look just like this. I'll just scribble out the e, and I'll say the predicted score on y, her y hat, would be equal to 8 plus -5 times 0. And 8 plus -5 times 0, that just becomes 0, that just becomes 8, so that shows that her predicted score on y is equal to 8. And that's the same thing we're saying up here, that each person's predicted score, that's how these equations work, that it will work out so that each person's predicted score is simply the mean for whatever group they're in. So if she's in group 0, the mean for group 0 is 8, so her predicted score is 8. And if she actually got a 7, well, she's 1 point below the predicted value. She's 1 point below the mean for group 0, so her error is going to be a -1, because she's 1 point below the group mean. She's 1 point below her predicted value. And so if we plug the numbers in for her, we have 7 is equal to 8, the mean for group 0, plus -5, the difference between groups, times 0, which is her score on x, plus -1, which is the error for that girl, for case number 7. And then for the second equations, for the equations for sampling error variance in a population, these are just identical to the ones we saw on the previous slide, because it's all looking at the same sample. We still have, for this sample, we have two parameter estimates. We have the mean for group 0 and the difference between the two means, and these are the equations for those two parameter estimates, and they are the same here as they were on the previous slide. So now we can consider how we can use these linear equations to answer the key questions at hand. We can answer a descriptive question, and we can answer an inferential question. And as before, the descriptive question is simply, what is the key parameter estimate? What's the key parameter estimate that we get in the sample? Now, as I've mentioned before, in this type of design, a two samples design where I'm looking at a contrast between two groups, we actually have two parameter estimates. One parameter estimate is the mean for group 0, that is the mean for our control group, and the other parameter estimate is the difference between the two means, the mean for group 1 minus the mean for group 0. And as I mentioned before, this first parameter estimate, the mean for our control group, is something we usually don't care about that much. We need it to make our equation work, but we usually don't have a particular research question that that parameter estimate is addressing, so we often don't care about it. So I'm going to just cross it out, because it's often something we don't care about that much in terms of it's not answering a crucial research question. The parameter estimate that we really care about is the difference between the two means, y bar 1 minus y bar 0. So that parameter estimate, y bar 1 minus y bar 0, that's the key parameter estimate that's answering that descriptive question. What is the size of the difference between the means of these two groups? How much do these two groups differ from each other? So that is the key parameter estimate that's answering that descriptive question. And now, what about that second question, the inferential question? The question about how well the results from our sample apply to the entire population. So recall that to address the inferential question, we've been using the errors from the equations involving sampling error variance in a population. And in this example, where we're doing a two samples test, doing a contrast between two groups, we have two different equations that are both equations for sampling error variance in a population. Because we have two parameter estimates, we have one equation for the parameter estimate that is the mean for our control group, and we have a second equation that's for the parameter estimate that's the difference between the two groups. And so we have this error that I'm circling right here, that's telling us how far the mean for the control group in our sample deviates from the true population parameter control group mean. And then we have this other error, the one that's in pink here that I'm circling now, that's the error for the difference that we got in our sample. That's how far the difference between means that we got in our sample deviates from the true population parameter difference between the two means. So we have these two errors. Now, in this situation, I mentioned that we really don't care that much about the mean for our control group. That's a parameter estimate that's usually not that important to us. It's not addressing an important research question. So I'm not going to bother to address an inferential statistic for that parameter estimate. And I've crossed it out here because we don't care about it that much. We could, if we wanted to, we could actually go through all the steps and do inferential statistics testing this mean for our control group. So we could if we wanted to, but I'm not going to because it's not going to do anything useful to us because we don't care about it. What we really care about is the parameter estimate that's the difference between the two means, and so that's where we want to do our inferential testing. We want to do our inferential statistic testing that difference between two means, so we're going to focus on the error from that very bottom equation, that E1 minus 0 SP. That's the error for the difference between the two means from sample S from population P. And as always, we can consider two different questions about that error, and I have that at the top of the page here. So that first question, what is the average deviation of the absolute values of those errors? And you should be able to answer that question because it's going to be the same answer as we've had all along here. What statistic? What statistic answers that question? What is the name of the statistic that is the average deviation of the absolute values of the errors? And of course, that will be the standard error of the statistic. In this case, it will be the standard error of the difference between two means. And then a second question, if the null hypothesis is true, what is the standardized error for this particular study? That is, if the null hypothesis is true, how much error do we make in this study measured in standardized units? And again, the answer to that question is something you should be able to answer because it's the same as it's always been. The answer to that is a t-value. A t-value tells you how much error you made in a study in standardized units if the null hypothesis is true. So let's take a closer look and see how we can calculate the standard error of our statistic and how we can calculate a t-value and do a t-test. I want to take a moment to clarify something that could be a potential source of confusion in the language that I use to describe the standard error of our statistics. So recall in the previous section when I was talking about a paired samples analysis, in that situation we were dealing with something called a difference score. Each case had two scores on the same x variable, and then we calculated a difference between those two scores, and then we calculated the average difference score, and we got the mean difference score. Now, in the two samples design, we're currently looking at a two samples design where we're going to test a contrast between two groups. And here we have two groups, and each group has a mean score, and we're looking at a difference between the two means for our two groups. We're looking at a difference between means. So if we go back to our paired samples analysis, in that situation with a paired samples analysis, the standard error of our statistic was the standard error of a difference score. And we could shorten that to simply call it the standard error of difference. Now, with the current example where I'm looking at a two samples analysis to test a contrast between two means, in this case, the standard error of our statistic is the standard error of a difference between means. Or if we wanted to, we could shorten that and simply call it the standard error of mean difference. That's a very common way to describe it, the standard error of mean difference. Now, this can be a little bit confusing because these terms all sound rather similar to each other. And moreover, I could potentially say the standard error of mean difference and maybe forget to say the word mean. And at that point, I'd be using the exact same language to describe the standard error of a difference between means that I'm using to describe the standard error of a difference score. So how can you keep these standard errors apart from each other? And probably the easiest way to keep them apart and to distinguish between them is to simply pay attention to context. Because if I'm talking about a paired sample situation, if we're talking about paired samples, well then the standard error of our statistic has to be the standard error of a difference score. And so anytime I'm talking about paired samples, you know that the standard error of the statistic will be a standard error of difference score. If we're dealing with a two samples analysis where I'm testing a contrast between two means from two different groups, in this situation, our standard error will always have to be the standard error of a difference between means, or what we could call the standard error of mean difference. And anytime we're dealing with a two samples analysis and we're going to make a contrast between two means, then our standard error of our statistic will always be the standard error of mean difference, or said more precisely, the standard error of difference between means. You could also pay attention to the notation that we use to describe each standard error. So when we were looking at a paired sample situation, our notation for the standard error of a difference score was SD subscript X bar difference. And that's the notation we use to indicate the standard error of a difference score. Now, with a two samples analysis, looking at a contrast between two groups, in this case, the standard error of a mean difference, we'll notate that with SD subscript Y bar minus Y bar. That stands for the Y bar, the mean for group 1, minus Y bar, the mean for our control group, the mean for our treatment group, minus the mean for our control group. So it's the standard deviation of the mean difference, Y bar minus Y bar. So now let's look at how we would calculate a t-value in a two samples design where we're making a contrast between two groups. And you will note that the process we use here is the same process we've been using all along to calculate a t-value. So here's the formula. So a t-value, what is a t-value equal to? Well, first we're going to take the parameter estimate from our sample, that is the statistic from our study, and in this case our parameter estimate will be the difference between the two means, the mean for group 1 minus the mean for group 0, the difference between the two means. So that's our parameter estimate. We're going to subtract from that the true population parameter, which we're going to assume is 0. We're going to assume the null hypothesis is true, so we're going to assume that in the population, the mean for group 1, that is mu for group 1, is the same as the mean for group 0, so that there's absolutely no difference between the two groups in the population. Mu1 minus mu 0, that is the mu for the treatment group, minus the mu for the control group, equals 0, meaning there's no difference between those two means. So we assume that the true population parameter is equal to 0. So we have our statistic minus the population parameter, which we assume is 0, and then we're going to divide that by the standard error of our statistic. In that case, it's going to be the standard error of mean difference, or the standard error of the difference between the two means. And as always, our equation is going to simplify to simply taking our statistic, our parameter estimate, in this case the difference between the two means, divided by the standard error of that statistic, in this case the standard error of mean difference. And as the pattern always goes, I say the t-score is calculated by taking a statistic, dividing it by its standard error. And then you say, well, I already know how to calculate the statistic. I can calculate the difference between two means, the mean for group 1 minus the mean for group 0. I can calculate that statistic, but how do I estimate the standard error of that statistic? And then you ask me, do I have a formula that I can give you that you could use to calculate the standard error of that statistic? And I say, why, yes, I do. So let's look at it. Here is a formula you can use to calculate the standard error of a mean difference. So here is the formula for the standard error of a mean difference. So I have here SD subscript y bar minus y bar. That's the standard error of the difference between two means. That is the standard error of mean difference. And it's going to be equal to the square root of, and then we're going to take something called the pooled variance, SD squared pooled, that stands for a pooled variance. And we're going to take this thing called a pooled variance and divide it by the sample size for group 1, and then take that same thing called a pooled variance and divide it by the sample size for group 2. So putting that all together, we take this thing called a pooled variance, divide it by sample size for group 1, and then we add to that the pooled variance divided by a sample size for group 2, and then we take the square root of all of that. Now, in order to complete this formula then, we need to understand what is this thing I'm calling the pooled variance and how do we calculate it. So we need to figure out how to calculate this thing I'm calling a pooled variance so that we can calculate the standard error of a mean difference. And here is a slide showing you how to calculate a pooled variance. Actually, on the left-hand side of the slide, I'm just reviewing the formula for a standard deviation. And then on the right-hand side of the slide, at the top, I have the formula for a pooled variance. And then below that, I have a formula for a pooled standard deviation. And right now, we need a pooled variance. We need to plug a pooled variance into our formula for the standard error of a mean difference. But later on, we're going to do some things where we'll need a pooled standard deviation, so I might as well talk about both of these things here all at once. And note that actually, we've already talked about a pooled standard deviation before. Recall that when I talked about a D statistic, I said that a D statistic was calculated by taking a difference between two means and then dividing that difference by a pooled standard deviation. So we've already talked about a pooled standard deviation. So let's clarify how all of these things are calculated. So first, let's just review how we calculate a standard deviation and then compare that to how we calculate a pooled variance and a pooled standard deviation. So at the top left here, I say SS is equal to the sum of y minus y bar squared. So that's the SS stands for sum of squares. And I just want to clarify, I'm going to use SS as a symbol for sum of squares so I don't have to write out this whole formula every place I need it. So I'm just going to use SS to stand for sum of squares. Notably, I'm not using X, but I'm using Y here because if we're calculating a pooled variance, we're talking about variance in the outcome variable. So for example, if I'm looking at a difference between two groups of children and how happy they are, well then happiness is the outcome variable, and I want to get the pooled variance for this outcome variable, happiness. And when I'm doing this two groups analysis, I'm going to call that outcome variable, variable Y. So that's why I have the letter Y here rather than the letter X. Usually when we talk about a standard deviation, we use the letter X, but if I'm talking about the variance for an outcome variable, which I'm calling Y, then I'm going to use the letter Y rather than the letter X. So the sum of Y minus Y bar squared and sum all those deviation scores up, that will give me the sum of squares. And then the variance is simply the sum of squares divided by my degrees of freedom. And then the standard deviation is I simply take the square root of that, the square root of the sum of squares divided by degrees of freedom. So that's just reviewing how we calculate a standard deviation. So now we can compare that to the formulas on the right. So the pooled variance is where I have two different groups, and each group will have its sum of squares, and each group will have its degrees of freedom. So if I'm just calculating the variance for one group, it's just simply the sum of squares divided by degrees of freedom. If I want to pool my variance across two groups, I'm going to take the sum of squares for group 1 plus the sum of squares for group 2 and divide that by the degrees of freedom for group 1 plus the degrees of freedom for group 2. So essentially, I'm going back to the sum of squares level to do my averaging, and by weighting each one by degrees of freedom, that means if I have groups of different sizes, they're going to be weighted differently. Recall that in my example that I'm showing you here, I showed you an example where I had exactly 4 children in each group, and the sample sizes were equal for each group. But it doesn't have to be that way. We could have one group that's large and one group that's small, and when we calculate our pooled variance, we would weight it so that if one group is large, it would have a larger degrees of freedom, and if another group is smaller, it would have a smaller degrees of freedom. So our pooled variance, we simply take the sum of squares for our two groups and add them together, and divide that by the degrees of freedom for our two groups added together, and that will give us our pooled variance. And then if we want to calculate a pooled standard deviation, we simply take the square root of our pooled variance, and that will give us a pooled standard deviation. And we need the pooled variance right now. Here we go. There, we need the pooled variance right now because we need this to calculate the standard error of mean difference. And we're going to need the pooled standard deviation later on because we're going to calculate a d-score pretty soon here. We're going to need to calculate a d-score to give us an effect size, and so we're going to need this pooled standard deviation to calculate our d statistic. And now you have everything you need to be able to calculate a t-value for a two samples study where you're making a contrast between two different groups. Now, to calculate your t-value, first you need to calculate your standard error of mean difference. So we first need to calculate our standard error of mean difference, and before we can do that, we first need to calculate our pooled variance. So the very first step is to calculate a pooled variance. And then, once I have calculated that pooled variance, I'm going to take that value I get for my pooled variance and plug it into two places in this formula for my standard error of a mean difference. So I put it right here. I'm circling one spot. I put it right there, and I put it right here. So two different places I put it in that formula. So then I'll take that pooled variance that I just calculated and divide it by the sample size for group 1, and I'll get that. And then I'll add to that, I'll take that exact same pooled variance, but this time divide it by the sample size for group 2, and I add these two together, and then I'll take the square root of all of that. Now, in our current example, if I have two groups that are exactly the same sample size, N1 and N2 would both be the same. But in most situations, we'll have different sample sizes, and the sample size for group 1 will not be the same as the sample size for group 2. So we plug all this in and we calculate our standard error of mean difference, and now we can take our standard error of mean difference and plug that into our formula for the t-value. So we take our statistic, our parameter estimate, in this case it's the difference between two means, and divide it by the standard error of that statistic, the standard error of the difference between two means, and that gives me my t-value. And once I have my t-value, I can then determine the probability of that t-value. I can determine what is the probability of getting a t-value this extreme if the null hypothesis is true. And we can look up the t-value probability. We can determine the probability by looking it up on a t-table, or using a probability calculator, or using software that would calculate the probability for us. And as always, to determine the probability of a t-value, we need two things. First, we need to know what our t-value is. We need to have our t-value, and we need to know our degrees of freedom. So we need to know our t-value and our degrees of freedom, because recall that the shape of the t-distribution, it changes shape just slightly depending on your degrees of freedom. So we need to know our t-value and degrees of freedom. So what are the degrees of freedom in a two-sample study making a contrast between two groups? I have the degrees of freedom down here at the bottom, And I've stated it two different ways, so you can take your pick, whichever way you like the best, you can choose that one and use it. So one way of saying it is this. I could say the degrees of freedom are equal to n minus 1 for group 1, that is the sample size for group 1 minus 1, plus the sample size for group 2 minus 1. You could think of that as the degrees of freedom for group 1 plus the degrees of freedom for group 2, and you add that together and you get your total degrees of freedom. Or if you want to, another way to think about the exact same thing, you could just say degrees of freedom is equal to your total sample size, group 1 plus group 2, minus 2. So either way, you get the exact same thing. You could say degrees of freedom is equal to your degrees of freedom for group 1 plus degrees of freedom for group 2, or you could simply say it's your total sample size minus 2. So degrees of freedom, so it's a little bit different. In previous situations, our degrees of freedom was always simply just n minus 1, but now we've got two groups. Essentially, we're calculating a mean for each of these two groups, and so because we have two groups, we're losing 2 degrees of freedom. So our degrees of freedom are now total sample size minus 2. And with that information, you could then determine the probability of your t-value. So let's use this hypothetical data set that we've been looking at and see how we could use this data set to calculate a t-value. And the first thing we need to calculate a t-value is we need to calculate the standard error of mean difference. And before we calculate the standard error of mean difference, we first need to calculate a pooled variance. So how do we calculate a pooled variance? Now, with this example, we've already previously calculated the mean for group 1, y bar for group 1. The mean for group 1 was a 3, and we calculated the mean for our control group for group 0, y bar for group 0 was 8. And so we could proceed and calculate a standard deviation for each group. So for example, for group 1, we have these 4 children in group 1, and we could take each of these scores on the y variable and subtract the mean from it. So 3 minus 3, 4 minus 3, 2 minus 3, 3 minus 3, and get each child's deviation score. And then we could square each of those deviations and sum it up to get the sum of squares. And it turns out that the sum of squares in that example would be equal to 2. And so then we could take our sum of squares and divide it by our degrees of freedom to get a variance. And in this example, the variance is equal to 0.67 with rounding. And then we could take the square root of our variance and get the standard deviation. And in this example, the standard deviation for group 1 comes out to be 0.82. Now, in real life, it would be pretty unusual to do a 2-sample study testing a contrast between two groups. It would be pretty unusual to do this type of study and have the same number of people in each group. Oftentimes we try to have the same number of people or the same number of cases in each group, but it rarely works out that way. So it would be unusual to have the same number of people in each group. And it would be even more unusual if each group had the exact same standard deviation. That would be nearly impossible, incredibly unrealistic. But as it turns out, that's the way I've created this hypothetical data set. I created a hypothetical data set where both groups are the same size and where both groups have the exact same standard deviation. So if we calculate the sum of squares for this second group, for the people in my control group, that is 8 and 8 and 7 and 9, and in this case we would subtract the mean from each score, so 8 minus 8, 8 minus 8, 7 minus 8, 9 minus 8, and then we square those deviations and sum the square deviations. We'll get a sum of squares equal to 2, and if we divide by degrees of freedom, we get 0.67, and our standard deviation, the square root of our variance, is 0.82. So I've created somewhat of an unrealistic situation here where both groups have the exact same sums of squares, they both have the same variance, so they both have the same standard deviation, and they both have the same sample size. That wouldn't really occur in real life, but it's what our hypothetical example looks like. So we can use this now to calculate our pooled variance. So I'll take the sum of squares for group 1, which was a 2, and add to that the sum of squares for group 2, which was also a 2. Usually these won't be the exact same value, but in my example it is. And then I'm going to add these two sums of squares together and divide it by the degrees of freedom for group 1, and it's going to be a sample of 4 people minus 1, so it's going to be a degrees of freedom of 3, plus the degrees of freedom for group 2, which again is 4 people minus 1, so it's a degrees of freedom of 3. So my equation then becomes 2 plus 2 divided by 3 plus 3, and that equals, with rounding, 0.667. So now 0.667, that's my pooled variance, and I can plug that into my formula for my standard error of mean difference. So for my standard error of mean difference, I need my pooled variance divided by n for sample 1, then I'm going to add to that my pooled variance divided by my sample size for group 2, and then take the square root. So let's do that. So I'll take my pooled variance, 0.667, and I'll take that value and I'll put it right there in that numerator, and I'll take that exact same value and put it right there, and this will always be the same. You'll calculate just a single pooled variance, and it will always be that you'll put that same exact value in these 2 spots in your formula for a standard error of mean difference. And then we're going to, in this left-hand side, we're going to take our pooled variance and divide it by the sample size for group 1, and that's 4. And then we're going to add to that, we'll take our pooled variance and divide it by our sample size for group 2. And so the 4's on the bottom of this equation, usually in real life, we've got 2 different groups with 2 different sample sizes. So usually these 2 values, the 2 4's in the equation, usually those would be different numbers in real life scenarios. Whereas our 2 numerators, 0.667, those will always be the same value. And by the way, when you calculate this formula, make sure you use the sample size and not your degrees of freedom. So for example, note that when we're calculating our pooled variance, we're using degrees of freedom in that formula, and then when we drop down to our formula for our standard error of the mean difference, then we're using sample size and not standard deviation, not degrees of freedom in that formula. So keep track of where we need degrees of freedom and where we're using just our total sample size. So I take 0.667 divided by 4 plus 0.667 divided by 4, add that together, take the square root, and my standard error of mean difference is 0.58. So that means if I replicate my study over and over and over again, that is, I get my, say for example, I get my sample of 8 children and randomly assign them to a treatment group and control group and calculate the size of difference between the 2 means. Each time I calculate that mean difference, the size of difference between 2 means, that mean difference is likely to deviate from the true population parameter by about 0.58 units. That's how much my mean difference will typically deviate from the true population parameter mean difference. That's the standard error of mean difference. So now that I've calculated that, let's see how we can plug that into our t formula and calculate our t value. And on this slide, down at the bottom, we have the calculation for the t value. And also on this slide, it provides a summary of everything we've been talking about in this unit. So up at the top, we have, here's the mean for our treatment group. The mean happiness score was a 3 for the treatment group, and the standard deviation was 0.82. And the mean for the control group, the mean happiness score for the control group was 8, and their standard deviation was 0.82. And then the key descriptive statistic, the key parameter estimate that we wanted to know in the study, was the difference between the 2 means, y bar 1 minus y bar 0. And that difference was -5. Our treatment group was 5 points below our control group. And then we have our linear equations that we're using to address the important questions at hand. The top linear equation, this is the equation for variance in a sample. And this has 2 parameter estimates. One parameter estimate is the mean for the control group, but we don't care about that parameter estimate too much. It doesn't really answer an important question. We need it for the equation, but it doesn't answer a key question. The parameter estimate we really care about is the difference between the 2 means, y bar 1 minus y bar 0. And again, that's our descriptive statistic. That's the one we really care about. And then we can also use these linear equations to answer the question, the inferential question, about how our results from our sample apply to the entire population. And the key thing we look at to address that question is this E1 minus 0 SP from this very bottom equation. So these two equations at the bottom here, those are both equations for sampling error variance in a population. We've got one is the sampling error variance for the mean for our control group, telling us how far the mean for the control group typically deviates from the true population parameter, but we don't care about that too much. That's not answering an important question, so we're not dealing with that too much. What we really care about is this very bottom equation, which is talking about how far the difference between the two means, the mean difference, how far does the mean difference from our sample typically deviate from the true population parameter mean difference. That's what we care about. And this E for this equation, E1 minus 0 SP, that tells us how far the mean difference from our sample deviates from the true population parameter. And we use this E to address a couple questions. One question is, what's the average size of these E's? If we replicate our study over and over and over an infinite number of times, how far on average does each study typically deviate from the true population parameter? How much does each mean difference from each study typically deviate from the true population parameter mean difference? And we just calculated that. That's given by the standard error of our statistic, or in this case, the standard error of the mean difference. And on the previous slide, we just calculated that and found that it was 0.58. So that's our standard error of mean difference. And now we can plug that into our t-score, and we can take our statistic from our study, our parameter. We got our parameter estimate was -5. So I'll take that -5, put it down here, divide it by the standard error of the mean difference, divide it by the standard error of our statistic. And as always, a t-value is always going to be a statistic divided by its standard error. And I get a t-value of -8.2. In other words, if the null hypothesis were true, then this study made more than 8 times the typical amount of error. So I've given you another example where we've made a substantial amount of error. And if we wanted to, we could then look up the probability of this. And if we did this, we'd need to know degrees of freedom. So we have a total of 8 people, and our degrees of freedom would be n minus 2. So our degrees of freedom would be 6. And if we were to go to a t-table or a t-calculator, we could say, what's the probability of getting a t-value of 8.62 or -8.62, which, by the way, we'd get the same thing either way. The probability of getting a t of +8.62 is the same as getting -0.62. So what's the probability of getting a t-value of 8.62 with 6 degrees of freedom? We could look that up, and we'd find it's a very small value. Our probability in this case is going to be less than 0.001. It's less than once in 1,000 would we get a t-value this extreme if the null hypothesis is true. So I've given you an example here with a very extreme t-value. Now, one thing to keep in mind here, one thing that might actually help as you're looking at t-values, you can keep in mind that usually a t-value becomes significant somewhere around 2. If you have a big sample, it's probably going to be a little bit less than 2. And if you have a really small sample, it might be slightly more than 2. But somewhere around the ballpark of t is equal to 2, we could actually call that a critical value. That's where things become significant. So anytime you calculate a t-value, just as a hint here, if you calculate a t-value and your t-value is larger than 2, chances are it's going to be significant. So in our t-value here, the probability is 0.001. It's less than 0.001. It's a very, very small probability. So this is definitely significant. That means we would reject the null hypothesis and claim to have detected a non-zero effect. The null hypothesis was that there was no difference between these two groups, that my treatment group had the exact same mean in the population as my control group. But in this study, if I get this significant t-value, I'd say this t-value, it's so large, it would be incredibly rare to get a t-value this large if the null hypothesis were really true. So we reject that null hypothesis, and we say we have a significant result, and we have detected a non-zero difference between these two groups. And this completes everything for Part C of Unit 3.